Another way to look at phase changes or changes in the states of matter is through phase diagrams. I call these butt diagrams because you got your like solid and liquid, and see where they meet. It looks like a butt crack, and you know, when you fart, you have a gas, which is the vapor at the butt crack, but that's just me. Before we get into this, I just want to clarify something that surprisingly has popped up in the past years in the multiple choice section of the AP exam, the difference between a physical change and a chemical change. And some of you are rolling your eyes because you think you know this, but I watched over 50% of students get this question wrong last year. So a physical change is where we are rearranging the particles, but we are not making or breaking bonds. So I just did liquid water in my before picture, and then in my after picture, I have water vapor. And a chemical change is where we actually make and break chemical bonds. So I started with the same liquid water picture, but then maybe we ran an electric current through it, and you're left with hydrogen and oxygen gas. So it is important to know that a phase change, when you change from one state to the other, that's a physical change. We're not actually making or breaking bonds. And again, you're probably rolling your eyes because it's really simple, and most of you would never say that when I freeze liquid water into solid ice cube that you're not, like, that you wouldn't say that it's not water anymore, but you'd be surprised at how many kids get that question wrong. They think they break bonds when you boil water, for example. Here's some simple vocab. Melting and freezing is solid to liquid, liquid to solid. Boiling and condensation is when we go from liquid to gas or gas to liquid. Two vocab words that might be new is sublimation, when we go straight from the solid phase to the gas phase, or deposition, when we go from the gas straight to the solid phase. So now let's talk about these butt diagrams or these phase diagrams. So what's helpful about these is we can look at the relationship between pressure and temperature and the different states of matter. So I do better when I can explain with an example. So let's say this is a phase diagram for water. The nice part about phase diagrams is if you know the temperature and the pressure of a substance, using this diagram you can figure out what state of matter the substance it is. So let's go with our standard. If we were at 1 atm pressure, notice pressure is graphed on the y-axis. So I got pressure here. If I'm at 1 atm, and we draw kind of a little dotted line, and we go to 0 degrees Celsius, where those lines intersect, we are right on the boundary between solid and liquid. And this one's actually a better example of the butt. You see, there's your butt crack. And then you got your vapor coming out. Great. Okay, so you see the butt diagram. So we're at the line, the boundary at the crack between solid and liquid. And that occurs right at standard pressure, 1 atmosphere, and 0 degrees Celsius. That we know that is the normal freezing point or melting point for water. So that slanted line, that's kind of the arrow is pointing at, is the line that represents the melting and freezing point. And in this case, the point where those two dotted lines intersect, that's at standard pressure, 1 atmosphere. So in this case, what I did is I extended this 1 atmosphere line all the way across, and I dropped, then once I hit the new line, I dropped it down, and you can actually predict what this temperature would be. At the boundary between liquid and vapor, that's where we're at here, we expect at 1 atmosphere our water to boil or to condense at 100 degrees Celsius. So I put in my 100 degrees Celsius. So what this means is that this kind of curved butt cheek that boundary line represents the boiling point or the temperature that we would condense if you're going the opposite direction. So using these boundaries, we can see all different kinds of phase changes. So if I look, so we got solid to liquid, that would be our melting. Liquid to solid, freezing. Liquid to vapor is our boiling. Vapor to liquid, that would be our condensing. We can also go straight from solid to vapor, and that's where we have sublimation, or when something sublimes. There is a special point where all three lines converge, and that's called the triple point, and I labeled it with that orange arrow. At the triple point, the solid, the liquid, and the gas all exist at the same point, and it's really actually something very amazing and cool. It doesn't happen usually under standard conditions. For water, it happens at a very low pressure and a very low temperature, and what you would see if you got to this point is you would see your liquid water with maybe some frozen pieces on top, and it's bubbling because some of it is boiling away. So super cool to see all three at once. Another special point I kind of pointed out with the arrow is called the critical point. So that's this guy right here. That's our critical point. And this is where we no longer have liquid and gas together like we did maybe at the boundary. So if you look, I have a pot of boiling water. And you can see that it's kind of steaming, so we have the liquid and the vapor existing at the same time. That's anywhere on this line, okay, depending on what the pressure is. At the critical point, liquid and gas are no longer together, and so we would be somewhere in this kind of outer region. And what happens at this point or past the critical point is we get a supercritical fluid. So we don't just go from liquid to gas. We get this kind of in between. There's no separation anymore between the liquid and the gas state. They're kind of like one thing with properties in between both a liquid and a gas. So a unique place to be hanging out. So again, I kind of hit these points already, but for those of you who like to write down your vocab words, that's the triple point and the critical point. So we can see where these phase changes would happen. So let's say I take a pot of regular water, that's my X right here, liquid water, at 1 atm pressure. So I'll kind of label in, let's stay at this 1 atm. 1 atm. And we just heat it up. So I'm going to keep pressure the same. We're still sitting in the same room. We heat it up, and you can see we're going to cross that boundary between liquid and vapor. We're going to boil this water. So that's one way we can change phase, is by changing the temperature. Another way we can change phases is by changing the pressure. So in this case, I'm going to leave the temperature alone. It's going to stay at the same value, but I'm going to change the pressure. So what I did here is I put a flask with water in it in a bell jar, and this jar, once it's sealed, I can lower the pressure by removing some air. So what we're doing here, we started at liquid. We're going to lower the pressure, drop down into the gas stage while keeping the temperature exactly the same. So changing temperature and changing pressure are two ways you can change the phases. I like this graph because it shows just all the kind of different things we talked about with the lines extended. So if you're a visual learner and need to see it all in one spot, these two green lines are representing two different substances, which I'm going to talk about in a second. So picture one of them would have this dotted green line as the solid to liquid boundary, and this one another liquid would have this solid, or another substance or chemical would have the solid green line as that boundary, and we'll talk about why that difference exists in a second. All right, so we have two different diagrams here, one for water on the left and one for carbon dioxide on the right. It's important to know that every substance has a unique looking phase diagram based off their properties. So not every phase diagram is identical. In fact, they're all different based off what chemical it's drawn for. So I want to just point out a couple things when comparing these. If you look at from 1 atm to 0 degrees, that's our boundary we talked about for boiling for water. That line that you see compared to the CO2, this line has a negative slope. It's slanted downwards to the right, whereas CO2, if we found the slope of its boundary between solid and liquid, it would have a positive slope. This is interesting because of the density of water. Water is very unique. Most substances are like carbon dioxide and will have a positive slope. But what that line is showing us is, and it explains why ice as a solid actually floats in its liquid version. Whereas most chemicals, if you take the solid version, it's going to sink in its liquid version because it's more dense. Whereas solid ice actually is less dense than liquid water. So super interesting factor there. Another piece that is interesting, if you take this 1 atmosphere line for carbon dioxide, you would expect at room temperature, or at standard pressure, you would expect to see that, I would expect to see that we would melt at some point, go straight from solid to liquid. But if you look, this boundary at 1 atm, which is standard pressure, it crosses straight from solid to gas. This is why we call carbon dioxide dry ice. So if you've ever messed around with dry ice, it's super fun. Be careful because it's very cold. But it goes straight from the solid to the gas phase, which is called sublimation. And you can see a picture down here. I put kind of that overflow of the gas phase, but we do have solid chunks of ice. And so just kind of a unique feature. And then the last piece I wanted to talk about is with water. we know that in Colorado, for example, where we have lower air pressure, the water will actually boil at a lower temperature, and you can see that on this graph, that as the pressure goes down, our temperature for where we're going to actually cross this boundary, right, as our pressure, so up here we're at higher pressure at a higher temperature, right? If we go to Colorado, lower pressure, we're going to actually boil at a lower temperature. So you can see why water boiling and the boiling point depends on, or it relies on the different pressures. All right, again, this topic is not something AP talks about a ton, but it could pop up in a multiple choice, so it's worth discussing in a short video.